This scientific paper titled, DNA Origami Tessellations, discusses the use of DNA origami nanostructures as building blocks for constructing tessellation patterns. The paper highlights that while DNA origami nanostructures are excellent for constructing tessellation patterns, their size and complexity are currently limited. The paper presents a general method for creating DNA origami tiles that can grow into tessellation patterns with precision and order at both the nanometer and micrometer scales. The authors identify the interhelical distance, d, as a critical design parameter that determines the conformation of the DNA origami tiles and the outcome of the tessellation pattern. By finely tuning d, the authors were able to accurately design the geometric shape of the monomer tiles, minimize curvature, and improve the tessellation capability. This enabled the formation of single crystalline lattices ranging from tens to hundreds of square micrometers. The study demonstrates the general applicability of the design method by presenting 9 tile geometries, 15 unique tile designs, and 12 tessellation patterns covering Platonic, Laves, and Archimedean tilings. The authors also explore strategies to increase the complexity of DNA origami tessellation, including reducing the symmetry of monomer tiles and co-assembling tiles of different geometries. These strategies resulted in various tiling patterns that rival Platonic tilings in size and quality. The authors emphasize that this study will promote DNA templated, programmable molecular and material patterning, and open up new opportunities for applications in metamaterial engineering, nanoelectronics, and nanolithography. In conclusion, this paper presents a method for creating DNA origami tiles that can grow into precise and ordered tessellation patterns. The authors demonstrate the applicability of the method to various tile geometries, resulting in the formation of single crystalline lattices with improved size and quality. The study highlights the potential of DNA origami tessellation for various applications in the field of nanotechnology. Provides an overview and the design workflow for DNA origami tessellation patterns. The figure is divided into several panels to illustrate the different steps of the design process. Panel A shows an overview of the study, highlighting the refined design parameters and the resulting tessellation patterns. The study involves the design of DNA origami tiles that self-assemble into tessellation patterns with micrometer scale order and nanometer scale precision. Panel B presents the design workflow for equilateral triangular tiling, which involves 5 steps. These steps include splitting the monomer tile into isosceles triangular subunits, depicting the subunit with parallel line segments, converting the line segments into DNA double helices, fitting 3 copies of the subunit together to create the prototypic tile, and finalizing the design by generating the scaffold strand and staple strands. Panel C illustrates the design workflow for chiral-pentagonal tiling, which requires a different splitting strategy and an additional reconfiguration step compared to equilateral triangular tiling. The monomer tile is split into 2 types of quadrilateral subunits, one square and one kite-shaped, which are then converted into line segments and DNA double helices. The isosceles triangular subunits are reconfigured to obtain the desired quadrilateral subunits by rotating 1/2 of the subunit around its apex. The complete tile is assembled from 2 copies of the square subunits and 3 copies of the kite-shaped subunits. Panel E shows an atomic force microscopy (AFM) image of a DNA origami tessellation pattern corresponding to the chiral-pentagonal tiling, demonstrating the nanometer scale precision of the pattern. Panel F presents a zoomed-out AFM image showing the micrometer scale order of the DNA origami tessellation pattern. This figure highlights the design workflow for creating DNA origami tiles and demonstrates the nanometer scale precision and micrometer scale order achieved in the tessellation patterns. The methods described in this figure are applicable to various tile geometries and can be used to construct tessellation patterns with different symmetries and complexities. Figure 2 in the paper describes the refinement of design parameters to minimize tile curvature in the DNA origami tessellation system. The figure shows the relationship between the interhelical distance, d, and the curvature of the tiles. 4 equilateral triangular tiles with different values of d ranging from 2.0 to 3.0 nanometers were designed and their curvature was quantitatively analyzed using a coarse-grained model. The results showed that the degree of tile curvature decreased initially as D increased from 2.0 to 2.5 nanometers, but then increased as D further increased to 3.0 nanometers. Based on experimental annealing results, the optimal range for D was determined to be 2.0 plus or minus 0.1 nanometers. The significance of Figure 2 is that it demonstrates the importance of the interhelical distance in minimizing tile curvature in the DNA origami tessellation system. By optimizing the design parameter D, the authors were able to improve the geometric design of the monomer tiles and reduce the reliance on curvature correction mechanisms. This allowed for the formation of high-quality, single crystalline lattices in the DNA origami tessellation, even without implementing curvature correction. These findings have important implications for the design and scalability of DNA origami tessellation systems, as well as for the development of programmable molecular and material patterning. Figure 3 of the paper shows the results of constructing regular tessellation patterns using DNA origami tiles. The optimized design parameters, particularly the interhelical distance, d, enabled the construction of micrometer-scale single crystalline lattices with nanometer-scale precision. The study demonstrated the versatility of the design method by creating regular tessellation patterns using different tile geometries, including equilateral triangles, squares, and regular hexagons. The resulting lattices ranged in size from tens to hundreds of square micrometers and exhibited high quality with nearly defect-free areas. The use of optimized design parameters reduced the dependence on curvature correction mechanisms, allowing for the formation of single crystalline lattices without rotational symmetry. This study expands the possibilities of DNA origami tessellation and opens up new opportunities for applications in metamaterial engineering, nanoelectronics, and nanolithography. Figure 4 of the paper describes the tessellation patterns assembled from low-symmetry DNA origami tiles. The figure shows 6 different tile geometries, including an isosceles right triangle, a rhombus, a kite, a prismatic pentagon, a chiropentagon, and a floret pentagon. For each tile geometry, the figure provides a schematic illustration of the monomer tile and the arrangement of tiles within the lattice. The figure also includes zoomed-in AFM images showing the detailed tile arrangement and intertile connections, a 1 micrometer x 1 micrometer AFM image showing a nearly defect-free area on the lattice, and a zoomed-out AFM image showing the size and overall quality of the crystalline lattice. The significance of Figure 4 is that it demonstrates the versatility of the DNA origami tessellation system by showing that it can be used to create tessellation patterns with low-symmetry tiles. The figure shows that the designed tiles can assemble into crystalline lattices with micrometer scale, nearly defect-free areas. This indicates that the optimized design parameters and bonding interactions are effective in achieving precise and ordered structures across multiple scales. The successful assembly of the low-symmetry tessellation patterns opens up new possibilities for creating complex and functional materials using DNA origami. Other figures that are useful to discuss include Figure 1, which provides an overview and workflow for DNA origami tessellation patterns, and Figures 2 and 3, which show the refinement of design parameters to minimize tile curvature and examples of regular tilings, respectively. These figures provide important background information and context for understanding the results and significance of Figure 4. Figure 5 in the paper shows several examples of tessellation patterns assembled from DNA origami tiles. The authors used a general method to create DNA origami tiles that grow into tessellation patterns with micrometer scale order and nanometer scale precision. By finely tuning the interhelical distance, d, they were able to accurately design the monomer tiles and improve the tessellation capability. The study demonstrated the general applicability of the design method by creating 9 different tile geometries, 15 unique tile designs, and 12 tessellation patterns covering Platonic, Laves, and Archimedean tilings. The optimized tessellation system produced single crystalline lattices ranging in size from tens to hundreds of square micrometers. The authors also explored strategies to increase the complexity of DNA origami tessellation, including reducing the symmetry of monomer tiles and co-assembling tiles of different geometries. The study opens up new opportunities for applications in metamaterial engineering, nanoelectronics, and nanolithography. This scientific paper presents a method for creating DNA origami tiles that can be assembled into tessellation patterns with micrometer scale order and nanometer scale precision. The authors identified the interhelical distance, d, as a critical design parameter that affects the conformation and tessellation outcome of the tiles. By finely tuning d, the authors were able to design monomer tiles with minimized curvature and improved tessellation capability. They demonstrated the general applicability of their design method by creating 12 unique tessellation patterns, including Platonic, Laves, and Archimedean tilings. The tessellation patterns were visualized using atomic force microscopy, AFM, and showed single crystalline lattices ranging from tens to hundreds of square micrometers in size. Additionally, the authors explored strategies to increase the complexity of DNA origami tessellation, including reducing the symmetry of monomer tiles and co-assembling tiles of different geometries. The study opens up new opportunities for applications in metamaterial engineering, nanoelectronics, and nanolithography. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.